Welcome to Calculus, a Red Pill course. This is lesson 1, where we introduce the universe of calculus. To give you an idea of what to expect, I should probably answer two questions at the outset. What is calculus and what is a red pill course? Calculus goes back to the infinitesimal calculus of Leibniz and Newton and can be described as the mathematical study of continuous change. There are two classical and related problems that calculus deals with. The first is that of the instantaneous rate of change. Suppose a car is accelerating in a straight line, and we have a function that specifies its position at any point in time. How can we define and calculate its instantaneous velocity at a given time? In geometric terms, how can we define and calculate the slope of a curve at a given point, where the curve is the position versus time graph? The second problem is the opposite question and deals with the accumulation of a quantity, where the rate of change is known at any point in time. For example, how can we determine the position of the car from its velocity versus time graph? In geometric terms, how can we find the area under the graph? The first problem leads to differential calculus, the second problem to integral calculus. However, the very first task of modern calculus is to find a suitable number system with which the two classical problems can be tackled. This will be the system of real numbers. In calculus, as in math in general, we talk about a universe of things like numbers, sets, functions, and so on. Mathematicians like to leave the question of whether this universe exists or not to the philosophers. However, they talk about the universe as if it did exist. They describe it by establishing axioms and deriving theorems from them. Platonists like Cantor believe that the universe of mathematics is real in some sense. Formalists like Hilbert believe that it is a fiction. But as long as the theory of the universe is interesting and without contradictions, it is a good fiction. The method is the same in both cases. State axioms using some primitive notions and the language of logic. Then derive theorems from the axioms using the inference rules of logic. For convenience, you may also define new terms that enrich the language. New terms can be used in theorems, and proven theorems can enable new definitions. And of course, you may use already proven theorems in the proofs of further theorems. This is the way math works. In calculus courses, you usually start with primitive notions such as real number, set, ordered pair, constants such as 0 and 1, the arithmetic operations plus and times, the order predicate less than, and the set theoretic predicate member of. These notions are not defined explicitly, but implicitly by the axioms, which are the basic statements of calculus. These are the axioms of real numbers and the axioms of sets and ordered pairs. We will also follow this path in this course, but why am I calling it a red pill course? I took the idea from the Matrix movie, of course. Imagine you're exploring a universe and everything you pick out of the universe is blue. You would probably think that everything in the universe is blue. Your language to describe the universe probably wouldn't even have a word for blue, because there would be no use for it. Now imagine a mysterious person, a person you've never seen on campus before, comes up to you and tells you that the universe you're exploring is actually very different than you think. He offers you a blue pill and a red pill and says, "Take the blue pill and you'll wake up tomorrow and you won't remember me. You will continue to explore your monochromatic blue universe without knowing the truth. But if you take the red pill, you will see the universe with different eyes. You will realize that it contains blue things and an abundance of non-blue things." What will you do? Well, you don't have to decide now, but at the end of this lesson 1 you have a choice. You can choose a blue pill course using any conventional calculus textbook, Or you can continue to follow this course, which will make you see the universe of calculus with different eyes. That's why I call it a red pill course. In Lesson 1, the blue and the red pill courses do not yet differ. As is usual in calculus courses, we will take an axiomatic approach to introducing the system of real numbers. That is, we will state axioms that real numbers satisfy, but we will not say what real numbers are. First of all, we want to calculate with real numbers and compare them as we are accustomed to doing with the naive rational numbers that we learned about at school. We formulate this in the field axioms and the order axioms. Furthermore, we want the real numbers to have a property that we call Dedekind completeness and that we specify with the completeness axiom. If we want to calculate with real numbers in the same way as with naive rational numbers, this means that we have two arithmetic operations plus and times, which are defined on the real numbers and obey the following rules. For any real numbers x, y, z, we have x plus y equals y plus x, and x times y equals y times x. These rules are known as the commutative property of addition and multiplication. X plus y grouped plus z equals x plus y plus z grouped. And x times y grouped times z equals x times y times z grouped. These rules are known as the associative property of addition and multiplication. X times y plus z grouped equals x times y plus x times z. This is called the distributive property. Furthermore, we have two different numbers 0 and 1 with the following properties. For any real number x, we have x plus 0 equals x and x times 1 equals x. So 0 is neutral with respect to plus and 1 is neutral with respect to times. Furthermore, for any real number x, there is a real number y such that x plus y equals 0. This number is uniquely determined, which follows from the previous axioms, and is denoted by negative x. It is called the additive inverse of x. And finally, for any non-zero real number x, there is a real number y such that x times y equals 1. This number is uniquely determined, which again follows from the previous axioms, and is denoted by x2 minus 1. It is called the multiplicative inverse, or the reciprocal of x. All these axioms together are the field axioms. They stipulate that the real numbers form a field. As usual, subtraction is defined as the addition of the additive inverse and division as multiplication by the multiplicative inverse. We also want the real numbers to be ordered linearly, just like the naive rational numbers, so that we can visualize them as points on a straight line. This means that we have a binary predicate less than, such that for all real numbers x and y, exactly one of the following relations applies. Either x is less than y, or x is equal to y, or y is less than x. Two different real numbers can therefore always be compared by less than in exactly one direction. For the binary predicate to be an order predicate, it must also have a property known as transitivity. That is, if x is less than y and y is less than z, then x is also less than z. As usual, z is positive means 0 is less than z, and z is negative means z is less than 0. We also define x is greater than y by y is less than x, and the non-strict order relations less than or equal to and greater than or equal to. By convention, negative numbers are shown to the left of 0 and positive numbers are shown to the right of 0 on the number line. The order predicate should also be compatible with the arithmetic operations plus and times in the following way. If x is less than y, then x plus z is less than y plus z. And if x is less than y and z is positive, then x times z is less than y times z. This means an inequality with less than is preserved if we add the same number on both sides. And it is also preserved if we multiply both sides by the same positive number. The axioms presented here are the order axioms. Together with the field axioms, they turn the real number system into an ordered field. We now come to a property that distinguishes the system of real numbers from the system of rational numbers. It is called Dedekind completeness, after the German mathematician Richard Dedekind, who was one of the inventors of real numbers. Imagine the real numbers as points on a straight line. The real numbers should have the following property. If we divide the set of real numbers into a left and a right part, then there is a real number that is either the greatest number of the left part or the least number of the right part. This number is unique because if there were two such numbers, one would have to be the greatest number of the left part and the other the least number of the right part. But then the arithmetic mean of the two numbers would not be contained in any of the parts. So this cannot be the case. This is also the reason why the right part cannot contain a least number if the left part contains a greatest number, and why the left part cannot contain a greatest number if the right part contains a least number. We call a partition of a linearly ordered set into a left and a right part, both non-empty of course, a cut. Dedekind completeness therefore means that every cut in the real numbers is produced by exactly one real number. It does not occur with real numbers that the left part does not contain a greatest number, nor the right part a least number. Such a situation would mean that the number system has a gap, but the real numbers should not have any gaps. Dedekind completeness is usually formulated somewhat differently, namely as the least upper bound property. A set A of real numbers is said to be bounded above if there is a real number u such that all members of A are less than or equal to u. Such a number is called an upper bound of A. The least upper bound property, which we postulate as the completeness axiom, states that every non-empty set A of real numbers that is bounded above has a least upper bound in the real numbers. This number is also called the supremum of A. Note that the supremum of A may or may not be a member of A. Every non-empty set A of real numbers bounded above is associated with a cut in the real numbers, where the left part contains all numbers that are less than or equal to some member of A, and the right part contains all other numbers, that is, all numbers that are greater than any member of A. The real number produced by this cut is the supremum of A. Let us summarize. The real numbers satisfy the following axioms: the field axioms, the order axioms, and the completeness axiom, that is, the least upper bound property. The real numbers thus form a Dedekind complete ordered field. Did you notice anything special about the completeness axiom? In its formulation, we no longer spoke only of real numbers, of the arithmetic operations plus and times and the order relation less than, but of certain sets of real numbers, namely non-empty sets that are bounded above. But how do we even know that any sets of real numbers exist? Obviously, we need a few more axioms to enable us to work with sets. So let's talk about sets. What is a set? Intuitively, it is any collection of things that we find in our universe. But it is also itself an object in our universe, namely a set. As it turns out, we have to be careful with the term any collection, otherwise contradictions may arise. See, for example, Russell's paradox on Wikipedia. Therefore, we will also establish axioms for sets that tell us which sets belong to our universe. The things grouped together in a set are called the elements or the members of the set. We write X in A if X is a member of A and otherwise X is not in A. A set is uniquely determined by its members. This means that two sets are equal if they have the same members. This is actually an axiom, the axiom of extensionality. For two sets A and B, we define A is a subset of B if every member of A is also a member of B. That is, if for all x, x in A implies x in B. We say A is a proper subset of B if A is a subset of B but not equal to B. Of course, we would like to be able to collect all real numbers in a set. We therefore state the following axiom. There is a set that contains exactly all real numbers. By extensionality, this set is uniquely determined and we denote it with a blackboard bold R. We call this axiom the axiom of the existence of R. We also want to be able to form subsets of R or any given set A by specifying a characteristic property of its members. This is guaranteed by the axiom of separation. Suppose that phi of x is a statement in the language of calculus. X is a free variable here, a placeholder for things in our universe. Depending on what you put in for x, phi of x may or may not be satisfied. The axiom of separation says, for every set A, there is a set B, whose members are exactly those x in A that satisfy phi of x. For the set B, we write this. By extensionality, it is well defined. Phi of x may also have parameters, that is, further free variables. The defined set B then depends on these parameters. We will now look at some examples. For any two real numbers a and b, we can define the closed real interval from a to b as the set of all x in R for which a is less than or equal to x and x is less than or equal to b. For any two sets A and B, we can define the intersection of A and B as the set of all x in A for which x is in B, and the set difference of A and B as the set of all x in A for which x is not in B. We can also define the empty set as the set of all x in R for which x is not equal to x. Since this condition cannot be satisfied, this set has no members. Sometimes we want to form not only the intersection of two sets, but the intersection of infinitely many sets. For example, the intersection of a sequence of nested intervals. In general, it should be possible to form the intersection of any non-empty set of sets. We call a set whose members are again sets a family of sets. Let F be a non-empty family of sets. Then there is a member of F, say the set A. By separation, we can define the intersection of F as the set of all x in A with the property that X is a member of each set of the family. That is, for all B in F we have X and B. Since a member of the intersection must be a member of each set of the family, the definition is independent of A. The intersection of F is therefore well defined. The question arises whether we can form the union of a family of sets analogous to the intersection. For this purpose, however, we need a new axiom, the axiom of union. For every family F of sets, there is a set that contains exactly the members of all sets in F. This set is called the union of F. Intuitively, the simplest way to define a set is to explicitly list its members. Although this seems obvious, it is not yet possible on the basis of the previous axioms, because until now we could only form such a set if we could separate out its members from a given set. We need a new axiom for the general case. However, it turns out that it is sufficient to demand that we can form a set from any two objects in our universe. This is done by the axiom of pairing. For all x, y, there is a set that has exactly the members x and y. This set is called the pair of x and y, and is written as x, y in curly brackets. Due to the axiom of extensionality, the order of x and y is irrelevant. We can now also define the union of two sets A and B. It is the union of the pair of A and B. If both members of a pair are the same, we get a singleton, a set with only one member. We define the singleton of X as the pair of X and X. We can then recursively define sets with 3, 4, 5 and more members. This allows us to combine any explicitly specified list of things in our universe into a set. The axiom of power set makes it possible to collect all subsets of a given set into a set. For all sets A, there is a set whose members are exactly all possible subsets of A. It is called the power set of A, denoted with P of A. Example: if A is the set with the members 0 and 1, then the power set of A has these members: the empty set, the two singletons with the members 0 or 1, and the entire set A. Now we have the necessary vocabulary to formulate the completeness axiom. For all members A of the power set of R, if A is non-empty and bounded above, then A has a least upper bound in R. The members of a set have no particular order. The pair of x and y and the pair of y and x are the same. Sometimes, however, we need the concept of an ordered pair, where the order of the entries is important. For example, if we want to specify a point in the plane by its Cartesian coordinates, then the order of the coordinates is important. The point with the coordinates 1, 3 and the point with the coordinates 3, 1 are different. We assume there is a binary operation on the universe that assigns to any two objects x and y an object x, y in parentheses called the ordered pair of x and y. We have thus said how we denote ordered pairs, but not what an ordered pair is, just as we have not said what a real number or what a set is. For the sake of simplicity, we introduce ordered pair as a primitive notion, although it could be defined using set-theoretic means. See, for example, ordered pair on Wikipedia. In an axiomatic approach, we then have to formulate the basic statements about ordered pairs as axioms. The axiom of ordered pairs states that for two ordered pairs to be equal, they must match in both entries. That is, if the ordered pairs x1, y1 and x2, y2 are equal, then x1 equals x2 and y1 equals y2. An ordered pair is also called a couple or a two-tuple. We can extend this notion recursively to n-tuples for n equals 3, 4, 5 and so on by nested ordered pairs. We also want to form the set of all ordered pairs with entries from two given sets according to the following axiom of Cartesian products. For all sets A and B, there is a set whose members are exactly the ordered pairs x, y, for which x is in A and y is in B. We denote this set with A cross B and call it the Cartesian product of A and B. Analogous to the n-tuples, we define the n-fold Cartesian product recursively. It is the set of all n-tuples with entries from the respective sets A1 to An. If all sets of the n-fold Cartesian product are the same set A, we also write A to the n for it. Let's summarize the axioms we've learned so far. We can divide them into two groups. In the first group, we have the axioms that deal with the real numbers, the field axioms, the order axioms, the completeness axiom, and the axiom of the existence of R. In the second group, we have the axioms that deal with sets and ordered pairs in general, the axioms of extensionality, separation, pairing, union, power set, ordered pairs, and Cartesian products. These axioms form the basis of calculus in the Blue Pill course. It is now time to look at some of the implications. Cartesian products can be used to define relations and functions. Let A and B be sets. Any subset R of A cross B is called a relation from A to B. If A is the set with the members 0, 1, 2, and B is the set with the members 7, 8, 9, then this set of ordered pairs is an example of a relation from A to B. We can visualize this relation with a diagram like this, where arrows connect the members of A and B that are related. The set of all x in A for which there is a y in B, such that the ordered pair x, y is in R, is called the domain of R. In our example, this is the set with the members 1 and 2. The set of all y in B, for which there is an x in A, such that the ordered pair x, y is in R, is called the range of R. In our example, this is the set with the members 7 and 8. In the diagram, the members of the domain are those where at least one arrow begins, and the members of the range are those where at least one arrow ends. The inverse relation of R is the relation in which the roles of A and B and the order of the entries x and y are reversed. In our example, it looks like this. In the diagram, the direction of the arrows is reversed. A relation f from A to B is called a mapping or function from A to B if for each x in A there is exactly one y in B such that the ordered pair x, y is in F. In this case, we write f from A to B, and usually f of x equals y, or f maps x to y instead of x, y is in F. A function could look like this, for example. If f is a function and f of x equals y, then y is called the image of x under f, and x is called a preimage of y under f. While each member of A has exactly one image, there may be members of B that have no preimage, like the star in B, or more than one preimage, like the square in B. We define some special properties of functions that are relevant for calculus and mathematics in general. function f from a to b is called surjective if each member of B has at least one preimage in A. It is called injective if each member of B has at most one preimage in A. And it is called bijective if it is surjective and injective. A bijection is a one-to-one correspondence between A and B. The identity function from A to A, which maps each member to itself, is of course bijective. For any bijection f from A to B, the inverse relation f2 minus 1 is a bijection from B to A. For any two bijections f from A to B and g from B to C, the composition g after f from A to C, which maps x to g of f of x, is also a bijection. Since bijections are one-to-one correspondences, they are used to compare sets in terms of size. Two sets A and B are called equipotent if there is a bijective function from A to B. Due to the properties of bijections that we have just learned, the equipotence of sets has the following properties, which are familiar from equivalence relations. It is reflexive, that is, every set A is equipotent to itself, because the identity on A is a bijection. It is symmetric. If A is equipotent to B, then B is also equipotent to A, because the inverse of a bijection is bijective. And it is transitive. If A is equipotent to B and B is equipotent to C, then A is also equipotent to C. This is because the composition of bijections is bijective. According to the field axioms, we know that the real numbers 0 and 1 exist, and that we can define further natural numbers, potentially infinitely many, by repeatedly adding 1. 2 is defined as 1 plus 1, 3 is defined as 2 plus 1, 4 is defined as 3 plus 1, and so on. But how can we define the set n of all natural numbers? Some calculus textbooks don't make a big deal out of it and simply define n is the set with members 1, 2, 3, and so on. But that's not really a definition, because what are the dots supposed to mean? We certainly cannot derive something like that from the axioms. So that attempt is out of the race. What we want to express by the dots is that n should have the following properties. 1 is a member of n, and for all x, if x is a member of n, then so is x plus 1. Such sets are called inductive. However, there are many inductive sets, for example the entire set R, or the set of all positive reals. What we still need to achieve is that n contains only those real numbers that are absolutely necessary for a set to be inductive. In other words, n should be the smallest inductive set. It should contain only those numbers that are members of each inductive set. This leads to the following definition, which we find in many textbooks. N is the intersection of the family of all inductive subsets of R. As a consequence, n is a subset of every inductive set. Once we have defined the natural numbers, we can also define integers and rational numbers. We define the set n0 as n union the singleton containing 0. The set Z of all integers as n0 union the set of all reals for which the additive inverse is in n. The set Q of all rational numbers as the set of all reals that are a quotient of an integer and a natural number. We introduce a suggestive notation for the set of all natural numbers that are less than or equal to n. That is, the naturals from 1 to n. Since this is a proper definition, the dots are not objectionable here. It is sometimes convenient to allow for the case n equals 0. The result is then the empty set. The fact that n is a subset of every inductive set implies the principle of mathematical induction. Suppose we want to prove that a statement phi of n, formulated in the language of calculus, holds for all n in n. To do that, we can proceed according to the following schema called the principle of mathematical induction. First, show phi of 1. This is called the base case. Then, show for any n in n, if phi of n, then phi of n plus 1. This is called the induction step. Why does this work? The principle of mathematical induction is a valid proof schema because, according to the axiom of separation, we can define the set A of all n in n that satisfy phi of n. The base case and the induction step prove that A is inductive. Hence, n is a subset of A, and hence phi of n holds for all n in n. The principle of mathematical induction can be varied by taking any integer instead of 1 as the base case, to show that a statement is valid from this point onwards. The principle of mathematical induction seems intuitively quite plausible. Note, however, that it follows from the axioms and the definition of the set n. Many statements about natural numbers can be proven using mathematical induction. In some cases, if more than one variable is involved, a nested induction must be used. Here are some examples that are not difficult to prove. Sums and products of natural numbers are natural numbers again. All natural numbers are positive. All natural numbers except one have a natural number as their predecessor. For all natural numbers m and n, if m is less than n, then m is less than or equal to n minus 1. So two different natural numbers differ by at least 1. If the set of all naturals from 1 to m and the set of all naturals from 1 to n are the same, then m and n must be the same. The set n is well ordered. That is, every non-empty subset of n has a least member. These statements are not usually proved in calculus courses, and so we will not prove them here either. However, it is important to realize that these statements are not self-evident, but a consequence of the axioms we have established for our theory. They cannot be justified by considering the naive counting numbers 1, 2, 3 and so on, which are only potentially infinite. The statements claim to hold for all members of the infinite set n, which is an object of our postulated universe. N is an actual or completed infinity and thus not a naive concept. In connection with the natural numbers, recursive definitions are often found. For example, we would like to define exponentiation of a real number b with natural numbers recursively as follows. b to the power of 1 is b, and b to the n plus 1 is b to the n times b. According to this rule, we can calculate b to the power of 1, 2, 3, and so on, potentially without end. But have we defined b to the n for all n in n? In other words, does this define a function from n to r that assigns to each n the nth power of b? This is not immediately clear. More general, let A be a non-empty set, B a member of A, and G a function from A to A. In our example of exponentiation, A was the set of the reals and G was the multiplication by B. Now we define f of 1 is b and f of n plus 1 is g of f of n. Again, we can calculate f of 1, f of 2, f of 3, and so on, potentially without end. And again, the question arises, does this define a function f from n to r? In other words, are recursive definitions of functions with domain n even possible? Note that this situation is different from our previous recursive definitions, where we only considered a potentially infinite number of cases, 1, 2, 3, and so on. Recall, for example, our definition of n-tuples, or sets with n given members. The good news is recursive definitions of functions with domain n are indeed possible, and this is due to the recursion theorem. This theorem states the following. Let A be a non-empty set, B a member of A, and G a function from A to A. Then there is exactly one function f from n to a, such that f of 1 is b and f of n plus 1 is g of f of n, for all n in n. The recursion theorem can be proved by mathematical induction. However, it is not usually proved in calculus courses, so we will not prove it here either. The recursion theorem guarantees that we can define a function from n to a set A by saying what f of 1 is and how we can obtain f of n plus 1 from f of n. A set A is called finite if there is n in n0 such that the set of all natural numbers from 1 to n is equipotent to A. The number n is called the cardinality of A. The empty set is included by this definition by the case n equals 0. The cardinality of a finite set is well defined because the set from 1 to m and the set from 1 to n are only equal if m and n are equal. Many theorems about finite sets are proved by mathematical induction on their cardinality. For example, the following. Any subset of a finite set is finite. Any union of two finite sets is finite. The power set of any finite set is finite. Any finite set of real numbers contains a minimum, that is a least number, and a maximum, that is a greatest number. To be clear, I'm not advocating that the induction proofs for all these plausible statements about natural numbers and finite sets should be explicitly demonstrated in calculus courses. But it is important to understand that all these statements follow from the axioms and can be proved by mathematical induction. And it may help to go through one or two examples explicitly. Most of these induction proofs are not very difficult. There is another property of the real numbers that is important in connection with the natural numbers, the Archimedean property. R has the Archimedean property, which means n is not bounded above in R. That is, for every real number x, there is a natural number n that is greater than x. The Archimedean property also means that for every positive real number x, there is some natural number n such that 1 over n is less than x. All we have to do is choose n greater than 1 over x. And for any positive reals x and y, there is some natural number n such that n times x is greater than y. Simply choose n greater than y over x. We can prove the Archimedean property by contradiction. That is, we assume that n is bounded above in R and show that this assumption leads to a contradiction and must therefore be false. Okay, suppose n is bounded above in R. According to the completeness axiom, there is then a least upper bound S of n. Since S is an upper bound, each natural number n is less than or equal to s. But then, for each natural number n plus 1 is also less than or equal to s, because n contains the successor of each of its members. Hence, each member of n is also less than or equal to s minus 1. Therefore, s minus 1 is also an upper bound of n, and s is not the least upper bound. A contradiction. So we must conclude that n is not bounded above. Traditionally, a number is said to be infinite if its absolute value is greater than any natural number. It is said to be infinitely small or infinitesimal if its absolute value is less than the reciprocal of any natural number. According to this definition, there are neither infinite numbers nor non-zero infinitesimals in R, because R has the Archimedean property. This is a great pity because, as Leibniz and Newton already knew, we could make very good use of infinite numbers and non-zero infinitesimals in calculus. For example, we could determine the slope of a curve at the quotient of its infinitesimal rise dy over an infinitesimal run dx. Or we could determine the area under a curve by adding the areas of an infinite number of strips whose width dx is infinitesimal. In view of the Archimedean property of the real numbers, this path seems to be ruled out. But mathematicians don't give up quite so easily. There are at least 3 ways out of this dilemma. The first option is to dispense with infinite and infinitesimal numbers and translate the problems of calculus into the language of limits that was developed by Weierstrass in the 1860s. And this is the path taken by conventional calculus courses, or as we call them, blue pill courses. However, many students find the language of limits difficult and not very intuitive. The second option is to extend the system of real numbers to the system of hyperreal numbers, a number system that has many properties in common with R, but contains infinite and infinitesimal numbers. This option was developed in the 1960s by Abram Robinson. It is also the basis of Keisler's famous textbook Elementary Calculus. The third, and in my opinion the most thrilling option, is to take the red pill and thereby gain a new view of the universe of calculus. This option makes use of the so-called internal set theory, which was developed by Edward Nelson in 1977. Mathematically, the red pill consists of a new primitive notion and 3 new axioms that allow us to see more. For example, we will recognize that R, and also n, contain numbers that are greater than any sum of ones. We call such numbers unlimited. And we can use the reciprocals of the unlimited numbers as non-zero infinitesimals. With these infinitesimals, we can do calculus in the similar way to Leibniz and Newton, but on a modern axiomatic basis and without having to extend the system of the real numbers. Now you have a choice. Which pill do you want to take? If you choose the red pill, lesson 2 awaits you.